Good afternoon, everyone. Happy National Engineering Month. Very happy to have you all here with us today. Before we get started, I just want to introduce two of my colleagues that are also part of the engineering department here at Blade Air, Luis and James. And I'm also going to have Ava helping me on the back end, running through the Q&A and any other technical support. Before we actually dive into the session, I want everyone to take a moment to take a deep breath in and now out. Now, have you ever really stopped to think about what's actually in the air that you just inhaled? We take around 20,000 breaths every single day. That's a lot of breaths. And each breath actually contains thousands of microscopic pollutants. And the reality is most of these pollutants in the air are invisible to the naked eye. So we don't even realize that we're inhaling all of them. However, air quality is often something that we overlook until it actually becomes a problem. This is why we're here today and to talk about the impact and the power of engineering for National Engineering Month. The quality of the air that we breathe not only plays a crucial role in our health and productivity, but also the efficiency of our buildings, which we're going to explore all of these things today and see how engineering is tackling these challenges. And I hope, and we all hope, that by the end of the session, you'll have a new perspective on the air around you and the exciting new technologies that are shaping the future of clean, breathable spaces. Just before we get into it, I want to acknowledge the land. So before we begin, just want to take a moment to acknowledge that we are coming to you from Toronto, which is in the Dish with One Spoon territory. We respectfully acknowledge the past and the present traditional stewards of the land and their unique role in the life of the region. Toronto is on the traditional territory of the Anishinaabe, the Haudenosaunee, and the Wendat peoples, and is covered by Treaty 13 with the Mississaugas of the Credit First Nation. We pay our respects to their elders past, present, and emerging. As settlers, we are grateful for the opportunity to work, play, and live in this territory. To kind of set the scene, and before we get into more of the technical stuff, we really want to develop the engineering fundamentals as to why indoor air quality matters. And the main problem is that it is an invisible challenge because you can't see the majority of these particles in the air that are causing issues, causing problems to human health. A little bit about me personally before we dive in too deep is I'm currently working as a product developer with Blade Air. I graduated from Queen's University with my bachelor in applied science and mechanical engineering. And personally, why I'm passionate about the field of engineering and really why I wanted to do this event for National Engineering Month is I think there's just so much power behind the problem solving and the creativity in the field of engineering. There's always going to be a new problem that needs to be solved in ways that you can make a difference and an impact in people's lives. And the second part is that continuous learning aspect. So I love that a lot of the answers today were about learning because I think just the field of engineering in general is amazing because you're going to come to work every day. Something that keeps me motivated is that I know I'm going to learn something new every single day, and every day is going to be a little bit different. Indoor air is actually 2 to 5 times more polluted than outdoor air. So this really sets the scene as to why indoor air quality is such a prevalent and important issue, because we're spending the majority of our time in the spot that is actually more polluted. When we talk about indoor air quality, it refers to the quality of the air essentially relating to the health and comfort of building occupants. We know that good indoor air quality intuitively, it's going to be better for your health, but also something that some of you might not know is that it can also increase productivity. And just to intro a little bit of some relatable things that I'm sure some of you have experienced one or two of these situations or symptoms from actually experiencing poor indoor air quality. So maybe you're waking up with a stuffy nose or dry throat, you cook something for dinner, and then that smell is just lingering in your house for hours. Maybe you decide to do a big spring clean with the nicer weather, but then you're spraying all these cleaning products into the air and you start to get a headache. Maybe you get some new furniture, you get a new couch or new carpet, and you smell all that strong new furniture chemicals. Those are all pollutants that are being released into the air. And last, maybe you're at the gym and it's really crowded, not great ventilation, and there's just so many people in a condensed space that you start to feel a little bit lightheaded. So these are all symptoms of having poor indoor air quality that sometimes you might not even realize that that's the cause. And one quick study that I wanted to mention about the productivity aspect is that there was actually a one-year study conducted across 6 countries by the Harvard T.H. Chan School of Public Health, and they found that higher levels of particles of pollutants in the air in combination with lower ventilation rates actually led to slower response times and reduced accuracy on these cognitive tests. So that just really shows the importance of prioritizing your indoor air quality. Now, when we talk about the particles that are actually floating around in the air and the fact that majority of them you're not going to be able to see, maybe some of the larger dust particles, but for the most part, they're invisible. And you can see this, I like this graphic here because since we're talking on such a microscopic scale, it might be hard to visualize. So you can see the sizes of these particles relative to each other, where on the largest end of the scale is a human hair. And even already, like if you look at a piece of your own hair, that's already quite small even to the naked eye. So from there, it just keeps on getting smaller. The first is going to be particulate matter. This is in the industry what is considered the most common type of pollutant, and it's made up of small pieces of solids and liquids. Next, we have gases. This can be things such as carbon dioxide, monoxide, nitrogen, and sulfur oxides. And the one I just wanted to point out a little bit is ozone, because it's going to come up again later in the presentation. And as some of you may know, ozone naturally cleans the air by breaking down our air pollutants, but at ground level, it can actually be harmful to human health and irritate respiratory systems, leading to other health issues. And actually, some electrical devices, such as air purifiers, a specific type of technologies of air purifiers and photocopiers can produce ozone. Next, we have biological, which I'm sure lots of us are familiar with, and actually, due to the pandemic, raised more awareness about indoor air quality because people really started to care about the transmission of virus through the air. So you're going to have mold and mildew growth in areas where you have poor humidity control. So you have those really damp indoor environments, that's going to promote the growth of mold and mildew. And then bacteria and viruses are going to be transmitted through the air in crowded or poorly ventilated spaces. And you can see, just one quick thing I want to point out is that those viruses and bacteria are on the smallest end of the scale in terms of size. And why that makes them so dangerous is because the smaller the particle, the more likely it's going to be able to bypass the body's natural defense mechanism. So not only is it you're going to inhale it and might get past, for example, like mucus and your nasal hairs are examples of the body's natural defense mechanisms. But once it's in your lungs, the very smallest of particles can actually get taken and transported into the bloodstream, which makes them inherently more harmful. The last one is called volatile organic compounds, or VOCs for short. And these are compounds specifically that easily evaporate at room temperature. And they're often associated with odors, so really strong smelling things such as cleaning products or paints. How is a filter actually going to be able to catch these particles? So essentially, I'm just going to very briefly go through this graphic and explain the different mechanisms as to how the particles or the dust particles are removed from the air as they pass through a filter. And most times, just to note, in air filtration, there's multiple different filtration mechanisms that work together to trap particles for varying, depending on the particle size and property. The first one you're going to see here is called sieving. This is the most basic. You can think of it, for example, a net or a mesh or something, a strainer, where the particle is getting caught simply because it's bigger than the gap between the two filter fibers. Next, we have 2, 3, and 4, and these mechanisms depend on the size of the particle. So depending on whether it's bigger or smaller, it's going to get caught a little bit differently. But as a basis, generally how it's working is that the reason these particles are getting stuck to the filter fibers is due to van der Waals forces, or the natural molecular forces and attraction between those microscopic particles and the filter fibers. So for impaction, you're going to have these larger particles, and due to their angular momentum, they struggle to change direction. You can see it's not following the airflow. So because of that, they crash into the fibers. Interception, these particles are getting smaller, so they do actually follow the airflow, but eventually they're going to graze or become tangent to the filter fibers and then again stick due to adhesion of the van der Waals forces. Last, you have diffusion, and this is for the smallest of particles. And essentially, this is based on a principle called Brownian motion, where the particles are so small that they're actually just crashing into the air molecules, making them eventually, due to this random motion, more likely to stick to the filter fibers. The last one, which is not mechanical, so this one is actually different because we're actively pulling the dust into the filter fiber instead of just relying on the chance that it's going to hit. So you can think of it at the most basic level, like a magnet where you have a positive charge and a negative charge, and they're going to attract to each other. Now, building on, this is the final step that we're going to build on for this section. So we learned about the different particles that pollute the air, the different ways in which they're caught, and now we're going to zoom out to a more macro scale where we're going to talk about the technologies that actually use all of these things to catch the particles. First, probably most of you have seen, or maybe you've changed out a filter in your house before that looks similar to this. These are the standard filters. They're most common in HVAC systems right now, and can be made out of different materials, aluminum, fiberglass, paper, depending on the application. The next technology, which I think is a pretty cool one, is called activated carbon. And essentially what happens with this one is targeting specifically VOCs or odors. So the different technologies target different either sizes or types of the pollutants in the air. And essentially the carbon goes through this activation process, which the goal of this process is to increase the surface area. And why we want to do that is because in this graphic here in the top right corner, we're getting adsorption. So a little bit different than absorption, which is when the particles are penetrating the surface. We're actually getting adsorption, where they're just sticking to the outside of the surface due to again, those natural molecular forces. So this is why optimizing the surface area is so important, because once we optimize the surface area, more surface area means we're going to be able to catch more particles before that gets saturated and we have to replace the filter. One cool fact, just to put it into perspective, is that 1 gram of activated carbon can actually have a surface area of up to 3,000 meters squared, which is around the size of half of a soccer field, which is crazy, just zooming in that much, and pretty cool. So very effective at removing those odors from the air. The next one, another cool one, targeting specifically bacteria and viruses. And when we look at the wavelengths over here, there's a specific wavelength called UVC, which is a subband of ultraviolet radiation ranging from, you can see here, 200 to 280 nanometers, that is used to sterilize the air. So essentially, it kills airborne bacteria and viruses by destroying their DNA structure. And one thing, though, about this technology is that it produces ozone. Next, we have ionization, and this is now using beyond just the mechanical filtration mechanisms. Now we're introducing the electrostatic aspect, where you're going to have dirty air coming in, then it gets charged by a high voltage electrode, this ionizer section. These particles are then charged and attracted to oppositely charged metal plates, where they get attracted and they stick instead of floating in the air. And over time, these plates collect enough particles that they need to be cleaned. So I just have a little video demonstration here. You can see the particles passing through, getting charged, and then they actually get actively pulled into those electrodes to capture them. Last is electrostatic. No ozone production in this one, which is a big benefit in the industry, because you have to go, if you do have a technology that produces ozone, you have to go through lots of processes and get certifications and meet regulations to prove that that you don't produce a harmful amount of ozone. And essentially, the difference with this one between ionization is that in ionization, instead of charging the particles in the air, we're actually delivering a charge to the filter media. So the actual fibers in the media are getting charged and basically causing them to align with the electric field. A good analogy is similar to how a compass needle aligns with the Earth's magnetic field, for example. One thing I wanted to show here, which is another benefit, you actually get this thing called dust agglomeration, where as the dust particles are approaching the filter media, they get charged, start sticking to each other. So then you get these bigger clumps that are then easier to catch through mechanical filtration mechanisms as well. Now, just to end off here, after talking about all of these cool technologies and power of engineering, what's the problem? As I've mentioned a few times, some of these technologies produce ozone, which is not ideal because it's harmful to human health. The other one that I haven't mentioned yet, and Luis will get into more, is that waste is a major issue. So most of these filters are single use and made of non-biodegradable materials. So when you take your filter out and you replace it, you just have to throw the whole thing out. So there's so many filters being put in landfills. The other half of that is energy consumption, which is a big concern. So I talk about throughout this, you want to prioritize the ability of the filter to remove these particles from the air. But on the other side, you also have to consider the pressure drop across the filter. So you don't want to have a filter media that's so dense that, for example, in the HVAC system, the fans and the blowers have to work so hard to push that air through the filter. Which again comes back to energy consumption. So on that note, I'm going to pass it over to Luis to dive into how engineering solutions are addressing these challenges for a cleaner, more energy efficient future.
So good afternoon, everyone. Thank you for joining us today, and special thanks to Macey for organizing all of this on the back end. I'm really excited to have you here, and I'll be talking about sustainability challenge and kind of an engineering approach to real life situation that we've taken here at Blade Air, but is certainly applicable in any industry and in all engineering approaches. So about myself, I'm Vice President of Engineering here at Blade Air. My background is I have a Bachelor of Aerospace Engineering from Toronto Metropolitan University, and I have about 10 years in product development and quality assurance. I'm also part of the TMU Board of Governors alumni candidate. So look forward to that vote coming up in the summer. It wouldn't be a webinar without some shameless plugging. So that's my shameless plug right there. So really to start, I want to give a background on kind of how we measure filtration efficiency, as I'll be referencing kind of these numbers throughout. But essentially, we use what's called a MERV rating to measure filter efficiency. And what that stands for is minimum efficiency reporting value. And it's really just a number scale to kind of give a rating to how well and a filter is at filtering out different types of particles. So if we can see things like a MERV 8 filter out 70 to 85% of particles in the 3 to 10 micron range, which is kind of these mold spores and other things. And then something like a MERV 13 is when you're able to start to filter out some of those smaller particles that are that Macey highlighted before, like bacteria and some of the tobacco smoke and some other much smaller particles. As a frame of reference, anything above a MERV 16 is what we would consider then a HEPA filter and that kind of filtration used, in hospitals and things of that nature. So really, I want to start with kind of a study case for the entire HVAC industry. And obviously, we had a big pandemic. There was a big change to kind of the way we saw how our air and how dirty it really was. So before the pandemic, existing indoor air quality standards basically required most buildings to just use what was a MERV 8 filtration. Obviously, with the pandemic and everybody getting sick, we kind of realized, okay, maybe MERV 8 filtration is not really as good or good enough to kind of meet our indoor air quality needs. And so, since the pandemic, more standards have come out, and basically it's a more common recommendation to use better filtrations such as MERV 13, which obviously we saw is much better at filtrating those smaller particles to better protect ourselves. There's also the other side on the ventilation, which we basically, as we ran through the data after the pandemic, we realized that places that had better airflow and good ventilation saw the least incidence of infection. Really, places that just basically had more air circulating, uh, people were less sick than in other areas. And so there were minimum ventilation standards, which is just basically what we recommend as a minimum airflow for comfort in a space. And so the industry said, hey, you know what? Maybe we need to have more air circulating. That's a solution to kind of keep us in a cleaner environment. And so, really, to summarize, it came down to better filters and more fresh outside air. I can kind of bring up what the problem is that we realized after our great and easy solutions. So first, looking at the ventilation side, we said, hey, let's bring in more fresh outdoor air. That's going to make it nice and clean. The problem is, as we kind of realized with the most recent wildfires the last couple of years, and just, there are many cities and large population centers that just have not the best quality of outdoor air. So the truth is that maybe when measuring against a pandemic, outdoor air is good because it's not contaminated. However, if there's like a wildfire or you're bringing a lot of smog in, it's not really healthy for the indoor environment per se. Another big thing to point out with outdoor air is that it needs to be preconditioned. What we mean by that is like, we live here in Canada. Maybe it's wintertime, it's negative 20 degrees outside. We can't just bring in this air and, nobody's going to be comfortable with negative 20 air coming in. Basically, we need to kind of heat this air and kind of get it in a nice humidity percentage before it's brought into the space. And this actually requires quite a lot of energy to do, and that's both in heating or cooling. And it's something that we have to really be aware of. And then finally, if we try to switch out new equipment, maybe bigger fans, bigger motors, this kind of equipment is quite expensive. And so it's sometimes not really practical to do in a lot of scenarios, especially when looking at like schools and other places that really are working on tight budgets already. And then when looking at the filtration side, what kind of was alluded to from the poll question is higher MERV filters introduce inefficiencies into the system. And those come in the form of generally higher pressure drops, which kind of trickle down the system and forces it to use more power, or in the worst of cases, even prevent airflow from happening at all. Another thing that happens with certain MERV 13 filters and higher efficiency filters is that sometimes they use sacrifiers or other things to kind of make it be higher filtration. However, as they start to pick up particles, they quickly degrade and lose the efficiency. So where you maybe start as say a MERV 13, you quickly go down into a MERV 10 or even a MERV 6 as the filter starts to pick up particles. And lastly, this is true for most filtration, is they do require replacements, and that does kind of create waste. Obviously, on our end, from Blade Air, we do try to keep sustainability focus, and so we're not big fans of creating waste and other things of the nature. So now that we know these problems, we start to kind of target the choke points or potential solutions. So one of the things you think about, especially from the ventilation, is like, okay, maybe we get bigger fans or more efficient motors, and those are certainly solutions that occur. So basically, if you have a bigger fan, you can push the air through those higher efficiency filters, or in the case of more efficient motors, maybe using electrically commuted motors can give you better control of how much power you use to move that air. Another option are smart control systems. So these are systems that maybe you only run the fans when there's people occupying the space, or perhaps they run harder when there's more people in the space by using controls such as CO2 sensors and things of that nature. And then there are things like energy recovery systems, which kind of help to use the already warm indoor air to preheat kind of the outside air and can save a lot of energy when trying to heat or cool down the air coming into a building. So as we kind of looked at these ideas, we thought, hey, what would be an optimal solution is looking at the actual filters in the system. For one, filters are required in all HVAC systems. So that means that if we find a solution to this, we can really tackle all different types of systems from something small in your home furnace, or maybe something of a larger nature that uses a lot of moves a lot of air, such as like data centers or big condos and malls even. Another thing, we pointed out that when filters have higher pressure drop, it does trickle down the system in terms of inefficiencies. But what that also means is that if we do solve that problem, the solution does also trickle down to the system. So if you alleviate that issue, you're really able to alleviate the issues in the larger system. And that speaks true for the waste issue that we kind of referenced. If we're able to tackle this waste, we can have a big impact in our case, our goal of better sustainability, but really just to help the planet and really reduce that kind of waste. So what we have here, if we look at the filters, is an opportunity for a low cost and high impact, since filters in a grand sense are a lot cheaper than buying a new furnace or a new new equipment, especially when looking at larger systems. So the solution that we came up with here at Blade Air, it was the electrostatic solution. And what really we describe it as is low pressure, high efficiency filtration. So we have a solid metal frame that kind of lives inside the duct and is able to stay the lifetime there. And instead of switching out the entire filter, you switch out only the pad inside. The neat thing about this pad is because we use a lower graded pad that's about a MERV 8, we then enhance it by running a charge through the dielectric media. By creating an electrostatic field, we have enhanced filtration. And so we really get about a MERV 13 filtration efficiency while only producing pressure drops of that of a MERV 8 or lower. So what we get is lower pressure drop, so it allows for older systems to run as originally designed. One problem that we saw was when we started to increase filtration to MERV 13 filters, systems that were designed to run with lower pressure systems basically were not able to run, and many fans actually weren't able to function properly. So we were able to tackle that. On newer systems that are better equipped to drive more airflow, we're able to maximize the efficiency that these systems ran in. And we're able to even reduce the peak loads, which is really the maximum amount of energy that's required to run a system. So essentially, for large buildings and things of that nature, we're able to reduce the amount of electricity that they pull from the grid, which is really a big issue that is becoming more apparent with AI and the like increasing in nature. And so lastly, it does maximize the lifetime of the equipment since the motors and the fans don't need to run as hard. These systems are really meant to run for 20, often 30 years. And so we allow the equipment to be able to reach those ages. And another thing that we were able to do was capture higher dust loading, which means we're able to capture more total amounts of particles, so you don't need to change the filters as much. And when we tie all of these solutions, we really had a very holistic approach to the sustainability aspect. Looking at the holistic sustainability, the permanent frame allows for changing of only the media, so that means we have less waste. The higher dust loading allows for fewer changeouts, so again, that adds to the less waste. In most cases, we are able to reduce swap outs by over 50%, which is over 50% saved just on less times that you need to replace the filters. The fewer changeouts then result in fewer deliveries. So if you think about that, that's CO2 from trucks that are being sent out. These are things that sometimes are not considered, but are very much a part of the carbon footprint of a product. One thing that I haven't mentioned yet is actually the media that we use is 70% recycled fiberglass. So we're always mindful to kind of, where possible, use materials that are more recyclable, and that helps to further reduce kind of the carbon footprint that we have on the environment. And finally, we're still looking at even further innovations, things like 100% biodegradable media and other sustainable materials, and even recycling programs, so that we can further reduce the carbon footprint and help the sustainability of the planet. Finally, I want to close my section by kind of pointing out what the savings impact that we had simply by switching out your filters. At the end of the day, the point is that as engineers, we found a simple solution to tackle that could have a big impact. So I've outlined a couple of projects here. A residential project that we did out in Brampton. It's a new condo building. And that one building, we expect it's being commissioned right now, and we expect to save about 94 megawatt hours a year, which is the equivalent of 7 powered homes, or the amount of CO2 removed by 96 trees over the span of a year. And then highlighting obviously what a commercial project does. This is just with one large client, and you can see the amount of megawatt hours is quite substantial, and an even bigger impact in CO2e, or tons of the CO2e removed. One thing to note here is the reason that the numbers are so high for this project is that this one was actually based out of Texas, and the energy that they use from their grid comes from a lot of burning fossil fuels. So any energy that's saved there, we really have a large impact. And really, the reason that I kind of highlight these projects is more to show what kind of impact a small solution brings. Obviously, we're focused here on indoor air and filter specifically, because that's what we work on at Blade Air. But really, this is an approach and the type of solution thinking that we encourage in all industries and in all engineers, because really simple solutions can have a really large impact. And that's really kind of what I hope everyone can take out of this presentation today. And so with that, I'll pass it on to my colleague James, who's going to talk about some other cool projects.
Hi there. So obviously we've spoken a lot about filtration today. That's what we do here at Blade Air. But I wanted to really round out the discussion by highlighting some other projects that are using technology to solve modern problems. So about me, I'm a product designer at Blade Air. I'm an alumni of Humber Polytechnic and the University of Windsor, where I studied mechanical engineering technology and then went on to get my bachelor's of engineering technology. If you're joining us from Humber, hello. And if you're considering the transfer program to university afterwards, I would highly recommend it. I've learned a lot there, really started my my journey into the industry. So I've been in the industry for about 4 years now, working on high efficiency air systems, now filtration, and I'm interested in sustainability and native ecology. So I really wanted to start with a problem statement, right? 40% of all energy we produce actually goes right into buildings. So this is just building operations. This is ventilation, air treating, heating and cooling. 40% of all energy we produce is used up by buildings. And now the United Nations expects this number to double, or the greenhouse gas emissions total to double, if nothing is done, because we're concentrating more and more people in the built environment. Buildings start aging and actually getting less efficient as they age, as that equipment, starts to run down. So there's a clear problem, right? How can we maintain a quality of living for an ever-increasing population while maintaining a sustainable future? And that's the problem that we're all trying to solve. In our case, we're using filtration, but there's many different technologies that can be done, right? Sometimes you can't filter the air. Sometimes you do need to ventilate. And when you do ventilate, you will need to temper that air somehow. So the problem starts with the energy balance. Energy is going to enter or leave your building through many different mechanisms that will change throughout the climate, throughout the use of the building and the building design. If this equation isn't balanced, if you have more energy in than energy out, or more energy out than more energy in, the indoor climate is unstable. It's going to start to get hot, going to start to get cold, and you will notice very quickly. You can see wherever we draw the system boundary, you're going to have energy crossing it, right? So in this case, you have heat losses due to conduction. So this is a winter example where the building is losing heat. But in the summer, the building would be gaining heat due to conduction, right? Because the environment is hotter outside than it is inside. But there's many different ways that these buildings are going to gain and lose energy. And our fundamental goal as engineers is to figure out where we can convert some of these less desirable forms of heat loss or gain and convert them into useful energy. Now, the problem is that a lot of the time, these heat losses are unconcentrated, right? Heat will naturally flow from hot to cold. So it's difficult to reclaim that energy because it's going to be exiting the system at a sort of lower quality state than it would be entering. So in order to convert some of these heat losses, use technology known as a heat pump. This operates on the principle that it's much more efficient to move heat around than it is to create it. Let's say you want to use a resistance heater to heat your building. So let's say your room is cold and you plug in your portable air heater. Now that's going to use electrical resistance. So if you put in 1 unit of energy, you're going to get 1 unit of heat. A heat pump really just moves heat to where it's needed. So if you put in 1 unit of energy, you can actually get up to about 4 units of heat. Now this seems like a free source of energy, but it's not. We're really just moving heat from where it's not needed or where it's abundant to where it is needed. It's actually the exact same way a fridge works, right? You have heat being taken from that cold space inside the fridge and then rejected to the warmer space outside. That's why if you ever fill your fridge on the back, it gets warm. It's exactly that concept of heat pump. The thing is they require an external source for heating, an external sink for cooling. So you need somewhere to grab the heat from or put the heat to. So let's talk about this. Lake Ontario is obviously a massive water body with a very stable temperature gradient. Now the city already pulls water out of the lake for our drinking water. What EnWave has done is actually use that temperature gradient, that source of cold from the lake, as a heat sink. You can see here, water is pulled from deep in the lake. They actually extended the pipes to 100 meters depth, about 5 kilometers offshore. So at this depth, the lake water is pretty consistently at 4 degrees Celsius year-round. We pull that water out, and then before sending it to the water treatment plant to be used as drinking water, we pass it over a heat exchanger. That heat exchanger rejects heat from several buildings in the city so that they can maintain cooling. So there's actually, as I mentioned, the biggest system of its kind in the world. And no heat is actually returned to the lake because all the water is used municipally. So we don't actually have to worry about the ecological effects of returning this waste heat from the city into the lake. It actually cools over 100 buildings. Some of the clients include the Scotiabank Arena, City Hall, and even the Fairmont Hotel. Each of these buildings has a smaller loop. You can see on the top there, the pink and blue have a smaller heat pump loop that uses the larger N-wave district cooling loop to reject heat. This way, they can use a much smaller system on the rooftop. They don't have to have it's much more efficient because water is a much more efficient heat transfer medium than air. So it actually displaces over 55 megawatts of energy per year from the city's grid, just by using the natural cooling of the lake instead of artificial cooling from, say, an air conditioning or a condensing tower, or an evaporating tower, rather. It's actually so popular that the city is now expanding it. But the problem is, obviously, the amount of water we can pull is tied to the city's water needs. So it's a very stable rate. During the day when it's hottest, the system can actually be at capacity. So we're rejecting as much heat as we reasonably can into that water. But overnight, it's the city's cooler, right? We don't need as much cooling. There's extra capacity in the system. So we have a problem. We have extra capacity in the system, but it's not at the right time. So how can we access this extra capacity? Well, the well, in fact. I couldn't find any documents to say this is the reason it's called the well, but I choose to believe it is. Underneath the building, they have a 2 million gallon water tank that they use for thermal storage. So overnight, when the deep lake cooling system is not running at peak, they can actually reject heat from this water tank into that deep lake cooling loop and chill the water. It actually chills down below freezing because it's a water propylene glycol mix. So you can actually cool it below zero. Then during the day when it's hotter, they can actually reject heat from the building into that water tank because they've already sort of stored up some cold. So that's a way that they have actually increased the capacity of the system without taking more water, just by accessing thermal storage. So wastewater energy recovery is a form of hydrothermal energy. So hydrothermal energy is really just accessing that thermal energy from deep underground, from really the latent formation of the earth and volcanic activity, radioactive decay, all produces heat deep underground that we can access. Now, Toronto doesn't really have a lot of volcanic activity, which I'm quite thankful for, but we do have an underground river of warm water. Yeah, it's Toronto's sewer system. So it actually stays between 17 and 20 degrees year-round. And that's all that energy is from people showering, flushing their toilet, doing laundry. Whenever you're flushing water down the drain that's being heated up, you're adding energy to that system. So this photo here is actually from the city. They've mapped out the pipes, and you can see what the average flow is, the average water temperature, and then how much cooling and heating capacity they have, because the city wants to encourage this type of system. So this can be both a heat source and a heat sink because it's cooler in the summer and warmer in the winter. So with that, I want to talk about the WET system. Stands for wastewater energy transfer because it can do both heating and cooling, as I mentioned. So what this does is it taps into the city's wastewater system. You can see in the bottom right of that picture, there's a large borehole, and that actually drills all the way down to the sewer where they can access that water. So they have a mechanical separator that separates the wastewater from the suspended solids. And then heat pumps are attached to that, and they source energy from that sieved wastewater. Now, it's totally sealed, several different loops, so you don't have to worry about smell, thankfully. But it powers Toronto's Western Hospital. So it's especially useful in energy-intensive buildings like a hospital. As we mentioned, we have both filtration and ventilation. Hospitals require much more ventilation and much more filtration as well, because they're often filled with sick people or people who are immunocompromised, right? They have they're very energy intensive, but there's not really anything you can do. We need that performance. So the system has 16 heat exchangers, making it one of the largest, or making it the largest in the world, I should say. Another photo here. The borehole is over 30 meters deep to access the sewer, and it's planned to deliver over 90% of the heating and cooling to Toronto's Western Hospital. Now it's going to enable the site to reduce their greenhouse gas emissions by an estimated 8,400 metric tons per year, just by using these heat pumps and sourcing heat that's already flowing through the city, right? Finding these sources and sinks where we can really take advantage of naturally occurring, well, semi-naturally occurring energy. And that's what we all do as engineers.
That was awesome. It was great to hear from you, James and Luis. And I think after hearing all of this, we can agree that at the core of all of these advancements is this fundamental engineering mindset where we talk about identifying problems, optimizing solutions, and creating a real world impact. Whether it's what we talked about at the beginning, rethinking traditional air filters, or again, designing entire buildings with sustainability in mind. The work being done today is really laying the foundation for a cleaner, more efficient future. If anybody wants to stick around for any pressing questions, now would be a good time if you have any questions.
That one question from Larry that we did have was, can electrostatic filters be washed? And I think any of you guys can take that one.
Yeah, I can start with that one. So our product specifically that we make at Blade Air, the Pro Filter, which is the electrostatic technology, essentially the actual media that you're taking out of the filter is you have to fully replace that. So you remove the old one and put in a new one. But the thing that is reusable is the frame. So you would just have to wipe down the frame. Maybe there's some excess dust buildup on the aluminum frame, but that part, yes, as long as it's not attached to power, obviously, but the actual media itself needs to be replaced. Just a final send off for kind of, first of all, thank you for spending this hour with us today. And I really hope that you did learn something new and maybe felt inspired. And I wanted to just share this quote. Sustainable development requires human ingenuity. People are the most important resource. So I think this kind of hits home what we've been talking about throughout the entire session today, and essentially emphasizing that by tapping into our creativity and problem-solving skills, regardless of any industry or career path that you take with engineering, you unlock this potential to drive meaningful change and actually help shape a sustainable world for future generations.
Thank you all for joining.
Thanks,
Thanks so
everyone.
much, everyone.